Okay, so one very important thing to consider is that we need to solve for the phase when we have x as a function of time. We are using this general equation, we're deriving a lot of other things. So again, like we said before, this is is the same as this a cosine of wt plus b sine of wt. They're the same, okay? And you can call these constants whatever you prefer. It's up to you. So, okay, what we're going to do here is we're going to derive equations for position, acceleration, and velocity. And we're deriving them symbolically here. So what we want to pay attention to is the fact that where the block starts before I release it actually does affect the phase of the position, acceleration, and velocity. Okay, when we're dealing with them as a function of time. So what does that mean? What am I talking about? So let me draw what's happening here. Okay, so I have this spring, right? And I have a block, I have some mass, okay? And this is, oops, sorry, I put the equal, so this is the equilibrium point. I should really draw them like that. I feel like it's actually not correct to sometimes put the line on the other side. That's my equilibrium point. Okay, and then I have it stretched right past the equilibrium point to some point that is some distance a away. So we're just going to measure this as the distance a, okay? And then I'm going to release it, okay? And I'm going to release it, and then it's going to oscillate back and forth by this positive or negative a, right? So it's going to go back and forth, okay? So, and this is where I pull it out too. Sorry, my A's don't totally line up with where my drawing is, but maybe we should say this is a little bit longer because my A looks like it's longer than the distance to the wall, and that's not supposed to be the case here. Okay, so I'm pulling it out and then I'm releasing it, okay? And I want to know how that affects my equation. So I'm going to use this because I care about this phase. So we talked about this a little bit before, but what that phase means is when I have a graph where I have like x of t with respect to time, notice that this is like a cosine graph. So I have a, negative a. What that phase does is the phase is a shift, okay? So if this is an initial function for, cosine, which means that it would start, right, intersecting with a, because the maximum value of cosine would be 1 at the origin. If I have some phase shift, what that's going to do is it's going to take my expression and like move it over, right, in some direction. So if it maybe by some pi over 2, maybe this way, maybe, whatever. So in this case, what I'm doing is I am pulling it some distance a away, okay? And then I'm letting it go and letting it oscillate. And so I want to know, figure out how that affects my phase so I can derive these expressions, right? So you should actually be able to find that phase angle on your own if you're given some initial conditions. Let's talk about how you would do that. Okay, so let's say, so I have my x of t. Let me get the right color here. Okay, so I am recording, right? Yeah, okay. Okay, so I have my x of t, right? X of t is equal to a cosine of wt plus v. So I kind of should be able to like tell what so the hint that I'm given, so this is t equals 0, right? So that means at t equals 0, my expression is equal to a. So at x of 0, right? So a cosine of 0 plus phi, right? Because I'm just plugging in t equals 0, is going to be equal to a. So a cosine of phi, right? Cosine of phi equals a, which means that cosine of phi is equal to 1. So there are different options, you know what I mean, to make cosine of phi equal to 1. But we know that we want it to be at the origin, right? So if it's at the origin, we're choosing this phase shift to be 0, right? Because we just have a cosine function and it's not like we're not moving at a particular distance from the origin. It's going to start here. So we're going to choose our phi equal to 0, right? So we're going to say phi equal to 0. And we know that phi is equal to 0 because we know that x of t is equal to a at some time 0. And we look at like, here's what our graph would look like, right? And so it's sometimes 0 if it's equal to a. Perfect. That's what we're looking for. Okay, so what's our expression here? So we know x of t is equal to a cosine of wt. Nice. Okay, so that simplifies things for us nicely, right? Okay, so this is our function for position. Cool. Okay, we know that we're dealing with simple harmonic motion here. We don't have friction on this surface. And we can say that w is equal to the square root of k over m, right? K over m. So we can say x of t is equal to a cosine of the square root of k over m times time. Okay, cool. So that is part A. So it asks us for the position. Next, we're going to look at the acceleration and the velocity. I'm going to do velocity first just because it's the first derivative here. All right. I have a little bit more in the solution than you guys would need, but I think that's okay. So then for our velocity, we're just going to take the derivative of with respect to position. So dx of t over dt. Sorry, I know you guys are just looking at the top of my head for most of this video. It's very exciting. And then, so just taking the derivative with respect to this. So we're going to end up with a times square root of k over m, right? Because we're doing the chain rule, negative, and then sine of square root of k over m. We could have solved this symbolically first and then plugged it in after, and that might be easier sometimes, but I just kind of want to show what's going on here. Okay, so cool. So that's our expression for velocity with respect to time. So we did the chain rule derivative, so derivative of the outside first, and then multiply by the derivative of the inside. Okay, B, C, and then let's do B. So we're going to take the derivative again, and this is equal to velocity as a function of time. So squared over second derivative of position with respect to time. It's equal to acceleration with respect to time, which is going to be, we're going to take the derivative of this guy again. So we're going to negative a, and then it's going to be the square root of k over m times the square root of k over m, right? Because chain rule again, so derivative of the outside and then the inside. So I just sort of took the constant out there, and then cosine square root of k over m times t. Let me just double check that there. And that is correct. So nice. So I think we're also asked to figure out the max here. No, I think we're not, but let's talk about what would the max be. K over m. And so times cosine of square root of k over m t. And we can also note that, so w squared here. So we know that a of t is going to be equal to, remember what our x was? Just relating our quantities here. Is going to be equal to negative w squared x, basically, right? Because like this is our expression for x, right? And then w is equal to the square root of k over m. Okay. So same thing here. This is the fully solved out version. So this is just kind of talking about how we can relate those quantities again and just looking at how to do the derivatives again here. The one important takeaway for this problem is how we are determining our phase angle, right? So our initial time 0 step and what the x position as a function of time graph looks like at that time 0 step is going to tell us a lot about how we figure out our phase angle. So let's go ahead and do one more example problem where we start with these initial conditions and then have to solve for our phase angle. So given a phase angle that's not equal to 0.